Now we're going to go to geodesics. Okay, so we've done parallel transport around any curve. And now there's a special type of curve. Okay. No, sorry, we don't need this. Okay, so geodesic, let's start there. A naive way of thinking about geodesic is it's the straightest possible line on a manifold. So if you're working on a sphere, you can't go straight, but you can go as straight as possible, and in the case of the sphere, it's giant circles. And that's what geodesics are. I think if you've been doing research in this a little bit, I gave you the equations of the geodesic, but you didn't know where it came from. Okay, and so most of the time when you learn differential geometry, you get this path to a geodesic rather than the one that you got given to start with. Okay, so the definition of a geodesic is, given a derivative operator, a geodesic is a curve whose tangent points in the same direction as itself when it's parallel transported. Okay, so remember we had the idea of you're given a curve, you have a vector on the curve, and you can parallel transport the vector along the curve, okay, that it changes as little as possible. So now a geodesic is that special curve that if you have the tangent vector and you parallel transport the tangent vector, okay, then it remains in the same direction as the tangent itself. And so the way you define a geodesic is you simply take the parallel transport equation, which is that part, you apply it to the tangent itself, and you say that that must be proportional to the tangent. Okay. So this is, remember your tangent is basically your coordinate, derivatives of your coordinates. Okay. And so you are basically applying a second derivative operator to that, so it's going to give you a second order equation in the parameter along the tangent. Okay, so that's your strict definition of a geodesic. Okay, and alpha is an arbitrary function to the curve. Okay, and so what you can also do is you can say, okay, I have my curve. Remember when we were going right back to the start where we had curves and we had parameters along the curve. There was a special type of parameterization that was your arc length parameterization. Okay? This expression is valid for any parameterization. Okay? But what is possible is you can take this expression, you can rechange the parameter of your curve, okay, so that alpha is 0. Okay, remember right at the start again, if we were arc length parameterized and we took the derivative of the tangent vector in the direction of the tangent, then it was 0 because the norm of the tangent vector was 1. Okay, so this is the equivalent of that. If we choose the parameterization so that alpha is 0, we effectively have our arc length parameterization. Okay, so the most general way of writing parallel transport is this, but there always exists a parameterization so that that is possible. Okay, and this parameterization in GR or differential geometry we call the affine parameterization. Okay, the arc length parameterization was developed before this was mature. Okay, but you are now going to recognize the formulas we got there. Okay, so for a specific chart psi, okay, the geodesic is mapped to a curve in Rn, okay, and the parallel transport equation basically implies that the components of this curve satisfy this differential equation. Okay, so I've literally gone and I have written out this parallel transport equation in the affine case. I've written out this equation and that is simply here. So we have t of mu applied to the gradient of t of mu. So it's simply d dt times gamma mu alpha v contracted with t mu t sigma. Okay, so this is what our parallel transport equation is in the case where our parameters are fine, where we summed over it. Okay, and remember your t mu is simply the derivative of your coordinates describing the curve. In other words, the derivative t mu is simply d dt of x of mu. Okay, so what you have over here is a second derivative of x of mu with respect to t plus a combination of a quadratic terms of your first derivative of x of mu with respect to t. Okay, and if you solve that second order equation, you have the geodesic equations. And now what I did with the Hamiltonian formalization that you guys use is basically I rewrote these 4 second order equations as 8 first order equations, which we then solved. Okay, so the straightest possible path obeys this. Okay, your components t of mu is simply the derivative of x of mu with respect to the parameter in the curve. Okay, and so our geodesic equations become, if you actually want to write them in terms of the components of the actual coordinates of the curve, it's simply d squared x of mu dt squared times that. And those are your geodesic equations. And a lot of trouble goes into solving them. Okay. So what this thing is, it's basically a coupled system of n ordinary differential equations, okay, for the n functions of coordinates. Okay, so in some sense, the geodesics are very elegantly defined if you know what parallel transport is. Okay, it literally is taking the curve, keeping it as straight as possible, and parallel transporting it along itself. And the idea of as straight as possible is true for absolutely any manifold. Okay, and so from ODE theory, you'd always guarantee that there's a unique solution and that it always exists for any initial value of x. And here, it's once again your initial conditions. You have to specify your initial point or your initial coordinates x of mu, so n of them. And because it's a second order equation, you have to specify the vector in which they're changing. So you have to specify dx mu dt when you start. Okay, and so for given a point in your manifold, okay, any tangent vector, TA, which is an element of your tangent space at P, there always exists a unique geodesic through P with tangent TA. Okay, so all the stuff we know of lines and curves and stuff is valid here. All the stuff we know of differential equations is valid. Once again, because we're using our chart to take us from the manifold to Rn, and then we can use everything we know in Rn. Okay, so a very basic example. Let's just do it. Geodesics on a two-sphere. So here's our metric for the two-sphere. Our non-vanishing Christoffel symbols, I hope I'm not giving you an answer to the problem set, but anyway, is... Well, then... Okay, so make sure you get them right. Okay, so our non-vanishing Christoffel symbols are those guys. Okay. Our geodesic equation is this. So let's actually go out and write it out. Okay, so what we have is our coordinates we can simply call theta and phi. So our first coordinate is the second derivative of theta with respect to lambda minus, okay, so it's mu is theta. Okay, so the only one with theta is phi, so it's minus gamma theta phi d phi d lambda squared. Okay, if you had a Christoffel symbol with theta, phi, theta, you would have added a second term over there. Okay, and so we substitute in our Christoffel symbol, and so we have this equation, so that's one of them. The second equation for phi, we simply equals to minus 2 gamma phi theta phi. Why is there 2? So we go back here, we write it out. So we have this Christoffel symbol, so it's phi up top here, and then we contract it, but we have phi, and we must contract it over everything. So it's phi theta phi, but we also, it's symmetric, okay? So we have the first one, phi theta, theta phi, and then we're going to have phi phi theta also added there, and this is where the factor of 2 comes from. Okay, so be sure you actually are doing a real sum over these indexes, and you take the fact that you can switch them, that there's a symmetry over there. So it's often the first couple of times you do it, write down before you substitute in your Christoffel symbols, take this expression, write it out for all your components. In other words, sum over this. So you'd have gamma mu phi, and then you could have theta and phi here, and then you go again gamma mu theta, and then you have theta and phi there. So you actually have 4 different components, and then make sure you're not missing one because of symmetry. Okay, so here's a minus 2. That's where you write it out there. And now you have to push the solve button. Those are your geodesic equations, and you have to solve them in a way that makes sense. Okay, so what do you do? Right, these are coupled differential equations. So here you have dd theta, and here you have a dd phi. So you can't work out the second derivative of theta unless you have this. Here you have dd phi, here you have phi, and here you have theta. Okay, so what would you do? You would try and find something where you can write down a complete differential. Okay, these things are never easy to solve. There are tricks for doing them. And there is experience, and there's Hamiltonian, there's other ways of writing them into first order form. But initially, especially for the 2-dimensional ones, you try and do clever things to try and get it. And one clever thing you can do is multiply it with, they call it an integrating factor. What I would say, suppose I multiply this thing with some factor. Okay, say f of lambda or f of theta and phi. Can I do it so that the whole thing is a differential? Okay, and so here you have cot is basically cos over sine. So if I multiply the whole thing through by sine squared, okay, then I have sine squared over here times cos times sine over here. And I have a 2. There's another clue there. Okay, so if I then take dd lambda of sine squared d theta d lambda, the first term, if I apply directly, then I have sine squared d theta d lambda. Okay, plus, if I apply the derivative operator here, I have dd lambda, so I have 2 sine theta cos theta d theta d lambda times d phi d lambda. So I actually have this expression. Okay, and so this expression is exactly equivalent to that one, and this one I can solve easily. Okay, so we can integrate that to give d phi d lambda is equals to a, we have that this thing is then equals to a constant. Okay, and then I have d phi d lambda is equals to a constant over sine squared theta. Is this one okay?
Can I do it on the board?
You want to do it on the board? You're welcome. Okay, so what we have then is that d phi d lambda is equals to k over sine squared theta. Then you can go in and you can put it in there. Okay, now that you've got what d phi d lambda is, pretty generally, you put it back into that expression, and you get that the second derivative of theta with respect to lambda is sine theta cos theta k over sine squared theta, squared, because you have a square in there. Okay, oops, now I jumped a bit fast. So that simply equals to k squared cos theta over sine to the 3. And that potentially, you want to take derivatives with respect to lambda there. And then I got scared. So then I said, okay, before I do this, let me do an easier problem. Okay, and this I actually strongly advise is look at special cases, but make sure they justified special cases. So if k is equals to 0, okay, and this is any constant, integrating constant we get. In the special case where k is equals to 0, then we're going to have, firstly, that phi is equals to a constant, because d phi d lambda is then 0. Okay, so then we're going to have phi equals to a constant c1, and we're going to have theta equals to a constant c2 lambda plus a c3. Okay, so in the special case where k is 0, we have a solution where phi remains constant and theta is equals to that. If k is not equals to 0, we've got to find another way of solving the problem. And the way of solving that problem is also a technique, I think, you should have come across, where you have second order equations as functions of theta. One thing you do is you recognize, if you've done Strogatz, that this is basically a potential problem. Right? You have there's a second derivative of a function is equals to a function of the thing. Okay. And then what you do is you can either just use Strogatz's methods and find your conservative system, or a more systematic way is you call p theta, write it as a first order system, d theta d lambda, okay, and then dp theta d lambda is simply dp theta d lambda d theta, dp theta d theta d theta d lambda, okay, and that's equals to p theta times dp theta d theta. Okay, and then you can go and you can substitute. This guy is basically the second derivative with respect to theta, and then you substitute that on the right, and on the left you basically have your this thing. Okay, so here you basically have dp theta squared d theta times a half is equals to that guy. Okay, so this dp theta d lambda you put in there, that's equals to p theta dp theta d theta, which is equals to a half derivative of p theta squared. And so we have dd theta of p theta squared is equals to that. And you can then integrate that. And this is effectively your potential function that appears in Strogatz. Okay, and then this guy you integrate with respect to theta, and you get that p theta squared is equals to an integrating constant minus k squared over sine theta, because the integral of this with respect to theta is simply, you've got the derivative at the top, so it's just k squared over sine squared theta with a minus in front. And so we now have the most general version of what p theta is. Okay, and so what we then can do is go on and say, fine, my d lambda is going to be equals to d phi sine squared theta k. Where does that come from? Back here. Okay. And so that is going to be equals to d phi, and then sine squared theta over k is also going to be equals to, from this expression here, where we have p theta, right, we can say fine, that's equals to d theta over the square root of this thing. Okay, so we have two expressions for d lambda, and then we can go and say fine, d phi is then equals to k d theta over this thing, and we can simplify it a bit, and we can integrate it, and then we can actually find what phi is in terms of theta. And the way we integrate it is we make a substitution of u equals to cot theta, right? Because we have a square in a square root, it's usually tan squared or cot squared that's coming in. So we say u equals to cot theta, and we put it in there, and then you're actually going to get the expression for absolutely every big circle on your manifold when you integrate this. Okay. So geodesics aren't simple, but there are methods of actually integrating it, and that unfortunately comes with practice. The more problems you see, the more problems you struggle with, the more tricks you learn to actually cope with them. But they are very intuitive things once you've got it. Right, I think I'm going to stop there. Yeah, I'm going to stop there. And then on tomorrow, we're going to do some more geodesics. Okay, so tomorrow at 9, take a look at this, come ask questions of where you're stuck, try the problems.